Hello everyone, this is Dr. Lennon, and we are continuing with the antiderivatives lecture today. So let's just recap. Last time we basically focused on finding antiderivatives of polynomials. Today we'll look at the other classes of functions. So we found the antiderivatives of polynomials. Which basically corresponded to a couple of rules. One, if, let's say, f of x is x to the n, then capital F of x equals x to the n plus 1 over n plus 1 plus a constant is the general antiderivative. Then we also mentioned two rules about integrals in general, that they're both additive and have a constant out property. So if you have the integral of two functions f of x plus g of x, you can integrate each function separately as the integral of f of x plus the integral of g of x. And if you have a constant multiplied by a function, you can pull that out of the integral and integrate the function and then just multiply the constant back afterwards. So these are the rules that we basically applied last time. So we want to start today by looking at the other classes of functions. Remember that notation, the elongated s followed by the dx just means find the antiderivative or the general antiderivative of whatever's inside. So for logarithmic functions, let's start there. So if we recall, we know a derivative formula for the natural log. So recall that the derivative of the natural log of x happens to be 1 over x. So that means, you might guess, well, if we were looking for the general antiderivative of 1 over x, it would be the natural log of x. And that is true, but there is one little thing. Recall that the domain of the natural log only makes sense if the inputs in question are positive values. 0 is not in the domain of either 1 over x or the natural log of x, so you don't have to worry about that. But if we're reversing the process, we do need to include an absolute value. So basically, the antiderivative rule is just the reverse. So if f of x is equal to 1 over x, then the antiderivative, capital F of x, would be the natural log of the absolute value of x plus a constant of integration there. So this is the general antiderivative. So the other class of functions we really care about are the exponential functions. And again, what we're going to do is we're going to look at the derivative rules and just try to reverse the process. So exponential functions. So let's think about the derivative rules first. So recall we had two derivative rules. So derivative rules. So the first of these was the continuous form. If you were trying to take the derivative of, say, e to some constant power times x, the derivative would be k times e to the kx. So that would be the derivative rule for continuous form exponential functions. And again, remember, that's one reason that e to the x is such a special function. As we'll see, it actually has itself as both a derivative and an antiderivative. So it's a unique function in that respect. So if k were just equal to 1, this derivative rule would say that the derivative of e to the x is in fact just e to the x. And if we look at the other form that could possibly be in, it's maybe a to the x, something that looks like that. And if you took the derivative, this one came out to the natural log of a times a to the x. So when you're doing the antiderivative rules, what you really want to do is you want to kind of reverse what's happening to the derivative, and really that's based on the constant. So for rule number 1, for the exponential part's always kind of remaining there, the e to the kx. But when you're doing the derivative, you're multiplying by this k. So if you're doing the antiderivative, you'd reverse that process and you would divide by that k. And similarly for rule number 2, since you're multiplying by the natural log of a, you would be dividing by the natural log of a in terms of finding the base. We'd also need to add a constant for the general antiderivative, but let's go ahead and look at some examples with numbers just to make this a little more clear. So compute the antiderivative of each function. So for a, let's say we have f of x is equal to e to the 3x. So as mentioned before, what we're going to do here is we're just going to take that same exponential function, but instead we're going to multiply it by 1/3, right? So the antiderivative rule is going to be the reverse of the derivative rule. And let's say we have a part b where we have g of x is equal to 7 to the x. Then capital G of x would have to look like, oh, I forgot my plus a constant for the part A if we're finding the general antiderivative. So g to the x would be 7 to the x divided by this natural log of 7, the natural log of the base there, plus the constant for integration. So that's essentially the rules applied to the functions, and you could check by taking the derivative. Notice the constants would vanish when taking the derivative, and the 3 you would multiply by for part A would cancel with the 1/3, and the natural log of 7 you would multiply by would cancel with the division of natural log of 7. So these are our antiderivative rules for exponential functions. So let's do them with all the letters instead. So the first one, this is with all the notation. If you're trying to find the antiderivative of e to the kx dx, then this is 1 over k times e to the kx plus your constant for integration. So in that example A above, k was just the number 3. And if you're doing the antiderivative of, say, a to the x dx, you're going to get 1 over the natural log of a times a to the x plus a constant of integration. Okay, so let's try a couple of examples, just reiterating these rules and using that new notation. So example, let's go ahead and compute the antiderivatives for each of the following. So A, let's say we have the antiderivative of e to the 0.4x plus 7 dx. Well, again, what we're going to do is we're just going to split this up into 2 antiderivatives. So the antiderivative rule of the first part is an exponential function, so that's e to the 0.4x divided by 0.4. And 7 is a polynomial. Remember, the antiderivative of any constant, we just adjoin an x to it. So the antiderivative of 7 is 7x, because the derivative of 7x is 7. And then we have plus our constant, and maybe you would want to simplify the 1 divided by 0.4 on the first part. That's the same as 2.5. You can check on your calculator. Times e to the 0.4x plus 7x plus a constant. Okay, and then B, let's look at one more. Let's say the antiderivative of 1.8 raised to the x minus 11 over x dx. So the first part is exponential rule number 2. We have 1.8 to the x, and we have to divide by the natural log of 1.8. And then the second part, remember 11 is the same as 11 times 1 over x, and we can remove the constant and then just think about the derivative of 1 over x, which is the antiderivative rule for the logarithm that we talked about. So that's times the natural log of the absolute value of x. And then we have plus a constant. So that's it for the main antiderivative rules that we're going to look at in this class. Let's move on to the connection to the concrete areas that we're talking about. So we're going to talk about the fundamental theorem of calculus. There are actually two parts to this, but in this class we're just going to be focusing on the second part, which deals with areas. The first part really tells us why the derivative and antiderivative are kind of inverse operations. But you might have a sense of that just from understanding how we found these antiderivative rules. So let's start with some hypotheses. Let's suppose f of x is a continuous function. Things that are continuous are nice and integrable. So then, if we have any antiderivative, capital F of x is any antiderivative. Doesn't matter which one you pick, and remember that's all they would ever differ by is a constant anyway. The net area, which we'll talk about in a minute, between f of x and the x-axis from x equals a to x equals b, so on some interval, is given by, so it's going to use the same integral notation, but we're going to have limits on it now, so that same antiderivative symbol, but now the limit a below and b above of f of x dx, it's actually given by the antiderivative with b plugged in minus the antiderivative with a plugged in, so capital F of b minus f of a. So this is really giving us a concrete way to compute the exact area. When we started looking at areas below curves, we found a way to approximate them with Riemann integrals, but this tells us if we actually know how to find the antiderivative, we can find exactly what that number should be. So let's kind of compare that. So let's recall so we did such an example. So using Riemann sums, we estimated the area below y equals x squared from x equals 1 to x equals 3 was something like 8.72. Right? Basically what we did, we had some curve, and we have this interval from 1 to 3, and then we divided it maybe into 4 parts, I can't remember, and then we looked at the areas of these rectangles and we said, okay, we can look at the left sum and then we can look at the right sum and shade those, and that gives an estimated area using left and right rectangles. You can do the left rectangles, the right rectangles, average them, and we said, okay, that area average came out to about 8.72. Let's try this approach with the fundamental theorem of calc. So let's use the fundamental theorem of calculus to find the exact value. So basically our area is given using this notation, the integral symbol from 1 to 3 of this x squared dx. So what we do is we find the antiderivative of x squared, and we can pick whichever one we want. So really what you do is you just always pick the constant to be 0 that you're adding to the end, because that's the easiest one to work with. It doesn't make anything more complicated. So this would be x cubed over 3, and we're going from 1 to 3. So then what the fundamental theorem does is it says, well, plug 3 in for x, so we'd get 3 cubed over 3, and then plug 1 in for x, and subtract. And we end up getting 26 over 3, or 8.66 repeating. something like 8.67. And that is the exact perfect area underneath. So notice our Riemann estimation that we had, 8.72, was pretty close, but this is the actual perfect value. And if you kept doing the Riemann analysis with more and more rectangles, you would eventually get closer and closer to this value of 8.67. So let's look at a couple more examples where we're just kind of computing these things. So these are known as definite integrals when you're trying to find these areas. So this kind of combines the practice of using the fundamental theorem with applying the antiderivative rules that we've just learned. So let's find the definite integral from 0 to 4 of 6x minus 5 dx. I think the textbook always uses parentheses around the integrand thing you're trying to integrate. I don't always. Some people are more particular about that. I just consider the function anything that's between the integral symbol and the differential, the dx. Okay, so what are we doing here? Well, it's a polynomial, so we just add 1 to the power of x if it has an x there, and then divide by that power. And then the 5, we just add an x on, and we're going to plug in those numbers and subtract. With polynomials, it's actually really nice. So 6 divided by 2 is 3, so this is just 3 times 4 squared minus 5 times 4. The nice part is whenever you have a polynomial and you're plugging something in that has a 0, it's just everything's going to vanish, right? Because you're plugging 0 in everywhere there's an x, so that part you're subtracting just comes out to 0. So this just finishes off as 28, and that would be your answer for part A there. So just using those polynomial rules. For part B here, let's look at maybe one more polynomial. So the antiderivative from 1 to 3 of 1 plus 2x minus 4x cubed. And these polynomials are pretty straightforward once you get the hang of the rule. So the antiderivative of 1 is just x. The antiderivative of 2x would be 2x squared divided by 2. So that just comes out to x squared. And then the antiderivative of 4x cubed. So x cubed would be x to the 4th over 4. And that 4 over 4 just becomes 1. So we get minus x to the 4th from 1 to 3. So then what happens here? Well, we get 3 plus 3 squared minus 3 to the 4th minus 1 plus 1 squared minus 1 to the 4th, and that comes out to minus 69 minus 1, which is minus 70. Okay, let's do just a few more that involve some of the other rules. Let's say maybe we have the antiderivative from 1 to 9 of 4 square root x dx. So again, remember a lot of times when you have radicals, it's worthwhile to convert them to their exponent notation. So the square root of x is the same as x to the 1/2. So this one, when you're finding the antiderivative, we've got a 4, and then we want to add 1 to the power. So we know the power 1 plus 1/2 is 3 over 2, but then we need to divide by 3 over 2, which is the same as multiplying by the reciprocal 2/3. So that's what we have here, and we're going from 9 to 1 still. So this is the same thing as 8/3 x to the 3/2 from 1 to 9. So then we can plug in the numbers and subtract. So we get 8/3 times 9 to the 3 over 2 minus 8/3 times 1 to the 3 over 2. And that comes out to 72 minus 8/3, which is 69.3 repeating. So whenever you have radicals, a lot of times your antiderivatives and the things you're computing are going to involve fractions. Let's go ahead and look at maybe some ones that involve some exponential. Let's say we're doing the antiderivative from 0 to 2.6 of 8.4 e to the 0.4. So they're using the letter t here, t dt. So the antiderivative rule is pretty straightforward here. Remember, we take that 8.4 e to the 0.4t, and we're just dividing by 0.4. So we're going from 0 to 2.6. And 8.4 divided by 0.4 just comes out to 21. So this is 21e to the 0.4 t from 2.6 from 0 to 2.6. So this comes out to 21e to the 0.4 times that 2.6 minus 21e, and then 0.4 times 0 is just going to leave us with e to the 0. So this comes out, if you round it 2 decimal places, to about 38.41. Okay, let's go ahead and look at one more. Maybe that involves something that looks a little more complicated. X cubed over 3x to the 6th over x to the 4th. So the thing here is we don't have any rule for antiderivative of quotients at this point. So we want to use algebra to try and simplify things. So x to the 4th is a common denominator, so we can look at each part over that x to the 4th and split up our fraction. And in doing so, we can simplify this integral before finding any antiderivatives. So this is really just the antiderivative of 1 over x plus 3x squared. So that simplifies things a bit. We know the antiderivative rule for 1 over x is the natural log of the absolute value of x. So we get the natural log of the absolute value of x plus x cubed, and we are going from 1 to 2 there. So we plug each of those in, so we get the natural log of 2 plus 2 to the 3rd power minus the natural log of 1, which just happens to be 0, plus 1 to the 3rd power. So this comes out to the natural log of 2 plus 7, which is about 7.69. Okay, so the one thing we didn't talk about yet is what does the antiderivative as net area mean? So what is meant by net area? So basically, some things. Above the x-axis is positive. Below the x-axis is negative. And the positive orientation is left to right. So we could look at an example with some values. So let's say we had some picture. So we're just going to compute each integral and we'll see how they connect. And this will give us a rudimentary understanding of what these things mean and how they connect to the actual areas. So let's say we have this picture. And I don't know. Let's just say it's something like this, and we're hitting the x-axis at all of these points. Let's say capital A, capital B, capital C, and capital D. And let's say we know the areas. Let's say we know this is 7, this one is 3, and this one is 5. So we can actually compute these areas. So let's say we're trying to find the integral starting at A and finishing at C. And let's say this function is called f of x, of say f of x dx. Well, what that means is we've got the two areas, 7 and the 3. The 7 is above the x-axis and the 3 is below, so we get 7 minus 3. Okay, and we can look at lots of these together. So you could look at, say, maybe the integral. We know the integral from, say, just a to b of f of x is 7. So that means you're starting at A and going from left to right, hence the positive orientation. But let's say I switch that up and maybe I flip my limits around and I started at B and I went to A. So if I did that, then I'm going in the reverse direction. I'm starting at B and going to A, and that is going to reverse my orientation, which is going to make my result, in that case, negative. And of course, if you wanted the complete area, what you could just do is you could say, okay, well, what if I did the integral from A to D of the absolute value of f of x dx? Well, that would make all parts positive. So you would have 7 plus 3 plus 5, which would give you your result of 15. And, you know, if you compared that maybe to the regular integral from A to D of f of x dx, again, you're getting 7, but the 3's under the x-axis, so it would come out like this, 7 minus 3 plus 5, so that would come out to 9. And then to be even more confusing, we could look at the integral starting at D and finishing at A, going in the reverse orientation from right to left rather than left to right, and then all the signs would change. So you'd start out with a negative 7, then your 3 would, instead of being negative, be positive, but your 5 would also be negative. So this would then come out to negative 9. So that's kind of what's meant by net area, and a lot of times our formula is doing that. So that's why in the first example with x squared we look at, everything came out positive. But here, when you have parts of the graph above and parts of the graph below, that's what's meant by net area. The parts above are counting as positive area, and the parts below are counting as negative area. And we'll come back to this, looking at several examples and looking at areas between curves in future sections. Anyway, for now, that's all. This is Dr. Lennon signing off.